Okay, so before moving on to the concept of a well-ordering, I should go back to the notion of an order-preserving function and state the definition of an isomorphism, which is a bijection such that both f and f inverse are order-preserving. That's an isomorphism. If an isomorphism maps from a set to itself, of course we call that an automorphism. Okay, on to the concept of a well-ordering. A set is called well-ordered if every non-empty subset has a least element. So obviously the set to have in mind for this concept is n. But also every subset of that, even the empty set, would also be a well-ordered set. The empty set just comes from vacuous quantification. But also we could take any subset of the integers that has a least element. That will also be a well-ordered set. Notice that the set of all non-negative rational numbers would have a least element, but it is not a well-ordered set because some subset of it does not have a least element, namely the open interval from 0 to 1. Okay, we will prove a first lemma about well-ordered sets. And in fact, I thought I had a little bit of an improvement on this proof, but of course an amateur would not actually have a better proof than a professional mathematician, so I eventually spotted my mistake and then corrected it, coming up with exactly the same proof that the author had. So, the lemma is that any well-ordered set with a function mapping it to itself that is increasing never maps an element to a lesser value, right? Always greater than or equal to. So, if we assume for contradiction that the set of all things that map to a lesser value is a non-empty set, that's exactly contrary to the lemma. So if we produce a contradiction from this assumption, we will have proved it. So we take this set to be non-empty. We take z to be its minimal element. Then we ask, what does the function do to z? Well, the function must map z to a lesser element because, after all, z is in x, and everything in x has this property. Well, for one thing, we know that z is the minimal element of x, and since f of z is less than that, it cannot be in x. But, so I had thought, since we have this inequation, this means that f of z is in x because it meets the condition for being in x, right? It satisfies that criteria. But no, that doesn't actually mean that f of z is in x. That means z is in x, and we already knew that. So, so that line of proof that I had before was wrong. But what you can do to show that f of z is in x, and thereby produce a contradiction, is to apply the function yet again, this time applying the function to both sides of this inequation, and use the fact that f is increasing, therefore, this inequality remains true after applying f to both sides. Now this satisfies the condition for being in x, and in particular it implies that the thing on the right hand side, f of z, is in x. And so that really does produce a contradiction between f of z not being in x and f of z being in x. Proof complete. More in the next video.